Hello everyone, welcome to Analog Circuit Design. This is Lecture 6. We're going to talk about MOSFET capacitances and small signal model. So small signal model is really important, and I'm Tae Kang. Here's acknowledgement again to my PhD advisor Michael Flynn from University of Michigan, and then my friend Dr. Sung Jung Lee, who's working in Qualcomm. Here's our class status. We've been through, so these are lecture 2 and lecture 4 for week 1 and 2, and then we lecture week 3. We're going to talk about MOSFET and then small signal model. And then finally, next week, we will see the actual circuit amplifier. Let's talk about MOSFET capacitances. So far, we haven't considered the capacitances for MOSFET, right? But this is actually how MOSFET has like capacitances. You know, capacitance between every pair of terminals. And it matters especially when we consider about high frequency operation. And then most of the case, our MOSFET will work in and operates in high frequency condition where we have to consider these capacitances. So again, these capacitances are really important in actual design. And the tricky part is that these caps are nonlinear. You know what it means? It means that depends on the voltage, depends on the like operating point, capacitance are changing. So what we do is we usually estimate like the linear cap at a certain operating point. Explain more detail about like why capacitance matter when in high frequency. So for example, in this case, so let's see in this case, let's say V in, the voltage V in moves to like this step. So step voltage, let's say there is just 1 volt and then 0 volt, right? What do you think about VG voltage? Assuming there is no capacitance, let's say no cap. What do you think? It just literally follows V in. They're the same because there's nothing related about time constants or whatever. But assuming that we have here, we suddenly have C capacitance. So here this is with capacitance, capacitor. So we'll do V in as like step function, V in 0 volt and then 1 volt. You know what happened for VG? Suddenly it shows some time constants here. Because since there is resistor, right? There is resistor and capacitance. So the voltage source cannot like charge VG abruptly. It needs some time because it needs some charge to fill. Because Q is CV, right? So V equal C over Q over C. So we need some charge to change the voltage. And that charge is defined only when there's capacitance. So that's why suddenly we see some like delay in signal. It means that we started to consider about time, and that's directly related to operating like speed, frequency. First, source drain overlap capacitance. So it means between gate and source and drain. So C4, C3 and C4. C3 we can represent it like W times LD times COX. So W is width. So this actually, well, it's a bad drawing. So this gate actually looks like this, and then this is W, right? So W times this LD, this overlap, gate to source, or drain. So WLD and then COX, that's like the parameter for capacitance. But can we just This can we just represent it this simply? No, we cannot, because we have this fringing capacitor. So we cannot use it because of fringing capacitance, because of this, um, this one. So what people do is just make it as like this kind of new parameter. It will include fringing capacitor and also this LD, this overlap, because this overlap length is usually decided by the technology. You know why? Because people try to make this as small as possible. We don't want this like this long. We don't want it because if you make it really, if you make the overlap really long, what happened? We'll see a lot of capacitance, and then capacitor usually we don't want it because it will hinder the high frequency operation. So this LD is usually technology dependent. Like so, okay. So in this case, why let's just ignore LD and then COX because there's like bunch of other fringing capacitors. So let's just lump everything to this COV. So that's why we say it like more elaborate calculation, like bunch of things. We just use a simple this COV, which is good for us, right? We don't have to care about we have to care less thing. Next one is channel substrate capacitance. This is not that important, I think. We usually care about this when only in like turn off a cutoff region when MOSFET is off. So when we want to see the CGB, we kind of calculate this series capacitance because here is G and then here is B. But I'll explain later, but we usually don't care about this capacitance when MOSFET operates. Here's drain to source substrate cap. And so here's source, drain to bulk. So this is the capacitance of the reverse bias source and drain implant to the substrate. And there are two components, junction and sidewall. You see junction means from here, from top to bottom, and then sidewall is literally the side. So for example, when we calculate it, this is kind of important. So see junction. Junction is I said the bottom part, right? So we make this area W times E and then junction, and then also we have to consider about sidewall. And there's how many sidewall? Total four sidewall. So W plus E times 2 and then C sidewall. The reason why I said drain source to substrate cap is important is it's actually related to the circuit design. This example is from Rajabi book. So let's see the circuit. The first one, this is a layout. We briefly cover how the layout looks like. I think it's really good to know about layout. So here, see, how does it look like? So seems like this is source and drain. Do you know the current flow? I mean, the direction of current? Current flows from here, right? Because this is the gate. The mid one, this is the gate, and then we learned that current flows from drain to source. And here's the E. So this transistor is with length L and width W. So W. And then how about this one? Interestingly, they look different because you see that the W is W over 2 it's like a half W, right? But you see that the source is on the outside, and then drain is in the middle, and they share a same gate voltage. So you see that here, it seems like they're disconnected. No, they are not disconnected because they're in a different layer. So it looks like source is connected here, and then gate is coming here. So you see, so these two are in different layers. So don't be confused. Gates are connected here in below. So what you can see is they actually looks like this if we represent it in schematic, and this is also W. So their circuit, their dimensions are the same. So can we say these are the like do they behave exactly same? No, they are not because they're these drains to source drain to substrate capacitor are different. So let's calculate it. In the first example, which corresponds to this A, so capacitance between drain to bulk, which is drain to substrate, is WE times CJ. What was CJ? CJ was the capacitance between bottom of the drain over and substrate. So we need area WE that corresponds to this. So we're looking at this capacitor, right? And then what about like the sidewall capacitance? Because we have four side, right? So what we do is that W plus E times 2 and then C sidewall. That's our first case A. And then what about B? They're different. First, C dB. Where's D? D is here, right? D is here. So first, junction capacitance. The area, what's the area? E times W over 2, NCJ. You see the difference? Here. They're not same. They're not the same. This B, this case has smaller capacitance. And what about the sidewall capacitance? Also, they're less because W is now half. So it decreases. And then source bulk, source substrate. So this part, okay, let me just delete it. And now we're looking at this part, right? And then we have two of it, right? So when we calculate it, we just multiply two. And then let's just focus on this one single part. They're the same, right? Because you see C junction is a function of area because it's a capacitance from the bottom of the drain and substrate. So they're the same because this is W over 2 and then here's E, so this is it. And then what about sidewall capacitor? Same, right? Same as this drain. So when we multiply 2, it becomes like this. Then what is better? Is A better or B better? Besides, the name of B, this kind of layout, we call this as folded layout, or we also say, oh, this MOSFET uses finger. There are two finger. This is just single finger. This is very, very widely used in layout. I mean, every layout use this because, as I said, for example, like there's 1 centimeter width NMOS. The way we can draw that is we just use a lot of fingers. So again, let's come back to the question. What is better? A better or B better in terms of capacitance? Let's see A first. Um, CDB, drain to bulk, and CDB in this folded structure. B, the folded one has definitely a better capacitance, I mean smaller capacitance, because you see this is half, and then this is not exactly half, but kind of half. Mostly this is half because W is usually a lot larger than E. Maybe not a lot, but like 4 times at least, I would say, or more than that. So it turns out that CDB, A has larger capacitance, so B is better. But how about CSB? Are they same? No, in CSB it's kind of opposite. In CSB, this junction capacitance, they're the same because their total area are the same. But how about this sidewall capacitance? Now, B has larger sidewall capacitances. So it turns out B has larger CSB. Does it make sense? Can we say it's worse, it's bad? Probably, but sometimes it's okay. Because when we see the circuit, NMOS, and source, sometimes source is usually connected to where? Ground. And where does bulk go? Bulk goes to ground too. So in this case, V source bulk is 0. We see this kind of situation a lot. So suddenly CSB doesn't matter because these two nodes are already connected, so we don't see a capacitance then. So we can say even though B has larger source bulk capacitance, since this source substrate capacitance doesn't matter sometimes because of this actual circuit connection, we usually say B is better. Well, anyway, usually B is the only way that we can draw sometimes if the width is really large. So, well, this is just a side story. As I said in the very beginning, the capacitances, these multiple capacitances, they have a different value, depends on their operating point, and that's kind of what makes the modeling complicated. So let's first see at the cutoff region. So in cutoff, we have C3 and C4, and then some of the C1, and source and drain are disconnected from channel. Gate bulk capacitance consists of a series combination of, so it means this one, C1 and C2. So in short, in cutoff region, this CGD and CGS is COV times W. We learned this, right? And then CGB, this is actually C1 parallel C2. Now in triode means linear region, which means gate is turned on. The gate voltage is larger than VTH. So we do have an inversion layer, which is composed of electron. What happened here is that this part, so gate channel capacitance. You know what's the capacitance? The capacitance is like a two conductor, which is not connected electrically, but two conductor, and then inside there's insulator, and those are capacitance, right? So channels are conductor, and gate is conductor. So what happened is these two looks like a capacitance, and then this capacitance, this is we call this as gate channel capacitance, which is WLCOX. So COX is the value of here, this one, this insulator, I mean passivation layer. that has COX characteristic. So, you know, the area of gate is W times L. So WLCOX is a gate channel capacitance. As I said, gate channel capacitance means this conductor, gate conductor, and channel conductor. And these are equally divided between GS and GD. So GD and GS becomes, this is their original capacitance, right? Overlap capacitance. Plus, they kind of share the gate capacitance. And what about this C1 and C2? I'm saying capacitance between gate and bulk. So we kind of ignore this part because we have channel inversion layer, and then it shields the charge movement between gate and bulk. So just ignore the C1 and C2 in triode and saturation region. We'll talk about saturation region. Now saturation region. This is even weird looking because you see that the channel is not symmetrical. Now channel has this triangle mode. So because they're not like symmetrical, the CGS and CGD are not the same. So for example, CGD, let's see CGD, they don't have any channel here. So CGD doesn't share anything from this gate to channel capacitance. So it's only like this overlap capacitance. And CGS, so CGS kind of take all of the gate channel capacitance, but not fully. It would take just 2/3 capacitance. There's some like proof. They say there's some calculation. But let's just accept it. So the key point here is that in saturation region, CGS, so here's CGD and CGS, they are not the same because the shape of channel. Even their like overlap capacitance are the same, but because of the shape of channel, which is not symmetric, the CGS has some more capacitance. Again, here the same, the C1 and C2, which is C gate to bulk, we still have channel, and that channel shield between a charge between gate and bulk, so we can just ignore CGB. This graph shows how the this gate source and gate drain capacitance changes. I think this is very confusing. I'm still confused about this graph, but let me just briefly summarize it. So we're talking about CGD and CGS in triode. I mean turn off in cutoff region. What did we say? Do we have gate and channel capacitance? No, we don't. So we only care about overlap capacitance. So this CGS and CGD are the same as this value. So that's our cutoff region. And in saturation region, and first of all, why saturation region comes first? We always talk about all cutoff and triode and then saturation. That's because we're looking at this VGS. What was the condition of saturation region? VGS minus VTH is larger than, no, actually opposite, is smaller than VDS, right? This is our saturation region condition. So so we need like smaller VGS. If VGS increases, then we will not satisfy the saturation region condition and we'll go to triode. That's why here off and then saturation region, because we're increasing VGS. So let's come back to the saturation region. In saturation region, what did we learn? We learned that the channel, so all matters here is that the between gate and channel capacitance. So this is like root cause. This capacitance make this kind of complicated graph. So keep in mind that. So in saturation region, the reason why CGS and CGD are different is because of gate channel capacitance, and it's unsymmetric because the channel looks like a triangle. So channel has pinch off, most of the channel inclined to source. So that's why VGS has larger capacitance by this amount, while CGD doesn't have any extra capacitances. Extra capacitance because pinch off. There's no channel next to drain. And then again, next is this triode. Triode, the channel looks how? They just looks symmetrical. They're just symmetric, so that's why they're kind of just sharing this gate channel capacitance equally. Here's a summary. CGB, gate to bulk. We said that in cutoff we have something. These are the series connection of the C1 and C2. But in linear saturation, we kind of ignore the CGB because of in linear saturation the channel appears because of the inversion. Well, inversion layer is channel, so because of the V gate voltage is high enough. So and then the inversion channel work as a shield, so there's no capacitance. And then CGD cutoff, we're just seeing these overlap capacitance, but in linear, we are dividing the gate to channel capacitance equally. But in saturation, the gate to drain capacitor doesn't see any like extra gate channel capacitance because you said, and then I said because of the unsymmetric shape of channel, because here again, because channel looks like this, and here's drain, and here is source. You see that the gate doesn't see any channel, so gate in saturation region, gate just this overlap capacitance. But in CGS, they're different. CGS in cutoff, well, they're the same. There's overlap capacitance. In linear, as I said, since channel looks like channel just is symmetric, they just share this, you know, this gate to channel capacitance. So that's here. And in saturation region, as I said, the source takes most of the channel. So they take like 2/3 of this gate channel capacitance. And also there's CSB and CDB. We learned that we need to, there is a junction capacitance, which is a bottom part of the drain or source. So we multiply it by area, and then there is a sidewall capacitance. It's literally the side of the drain or source. And then we also learned that this source to substrate, this CSB or the CDB can be different, depends on how we draw a layout. Now MOSFET small signal model, this is very important. We will just use it all the time. Capacitance, that's also important, but that's kind of, we're not that using it directly in circuit design, but this small signal model we always use. So this is a very important part. So we have to be very used to it before our actual circuit part. What is small signal analysis? I mean, why do we care about that? Oh, besides, the small signal analysis is related to AC simulation. So linear circuits are easy to analyze. It's really, for example, like here, the like VRI. This is linear. Well, not VRV. VRI. This is linear. If you double the voltage, double the current because resistor is a constant. But in MOSFET, we usually don't see any linearity because this resistance, they're changing. But we like linear circuit because it's easy. So we want to ignore non-linearity. But can we? Can we ignore non-linearity? And in this example, let's see, this is just a IV curve of MOSFET, right? And then this part is saturation region. Do you think VDS and ID are in linear relationship? Kind of, right? It's kind of linear, but not in this case. Well, actually, we can also model this part too linear, but I'm just saying is in saturation region, it seems like a linear, I mean, at least linear than this part. So, and then most of the circuit MOSFET will operate in saturation region. So maybe we can kind of just model the MOSFET as linear. Here's a rule. How can we model the actual circuit as linear circuit? First, find quiescent points. It means that find like steady state point. We will talk about it later. So it means that most of the analog circuit, their operating point is kind of fixed. Like for example, in the amplifier, I mean, I'm not saying not every circuit. Some circuit, like for example, like ring oscillator, some kind of circuit doesn't show like quiescent points, but like some just amplifier or something like that, or current source, they most of the time they operate in a like steadily. They are not changing their current or voltage that much. So we will find kind of a steady state of the circuit, and then at that point we will replace components with linear circuits. Do you remember that when we talk about capacitances? In capacitors, there in the MOSFET there's three operating region, right? Cutoff, linear, saturation. And when we think what about like CGD, capacitance to from gate to drain? That value changes depends on what the regions in the MOSFETs are in, right? So if the MOSFET operates, if its operating region changes every time, it's really hard to model them because, as I said, capacitances are changing depends on the region. But in most of the analog circuit, do you think the region of MOSFET, the operation of MOSFET changes? No, they're not. They're just stuck at a single operating point. I'm not saying every time, but lots of time. Usually the MOSFET stays in a single region. At that time, if that's the case, capacitances are kind of constant. Finally, the non-linear capacitors becomes kind of a constant linear elements. That's what they're saying. So find quiescent point. It means that the operating region of the MOSFET is not changing. They're kind of steady. And then once they're like stable, substitute those non-linear capacitors or resistor to just normal capacitors and resistor. And then third, solve for small signal excitation. We'll see what it means. So it says our input is also small signal, and it's related to AC simulation. We'll look more detail. But just side question. What about digital circuits? Digital circuits is kind of hard to apply small signal because, for example, well, we haven't talked about this, but this is how inverter looks like. Okay, just assume that this is inverter. What it does is if input comes, the output is operating in the opposite way. And they're just operating like 0 to VDD, VDD to 0. This is how digital circuit operates usually. In this case, for example, this NMOS. At the starting, this voltage was 0, so NMOS is turned off. But suddenly it shows a transition to VDD, so NMOS suddenly turns on. Its operating region changes. At the very first time, the operation region was cut off, but it changes to what? Linear. So in digital circuit, it's kind of hard to apply small signal model because the MOSFET's operating region changes. In small signal model, we change components to linear components. And these are the example of linear components: resistor, capacitor, inductor, and voltage source and current source. So these are appeared in small signal model. But there's few more things, dependent sources. So for example, like voltage controlled current source. What it means is that like here there is current, and then let's say this current flows like V1, okay? And maybe like somewhere in the circuit, and then there is some like V1. So dependent sources means that it's kind of an active circuit that it measures some, for example, like voltage controlled, some voltage from somewhere, and then apply the amount of current here. We'll see dependent sources, especially this one, in our MOSFET small signal model. So we'll use it all the time. To change the circuit to small signal model, what was the first thing we should do? We need to find the quiescent operating point for the circuit. So here I'll explain what it means actually. So let's say there's a circuit. This is a common source amplifier. We haven't learned it. So at this moment, it's okay. We don't have to understand the operation here. But the point here is that, so this is antenna. This is antenna. And then the input is really small, like sometimes even less than 1 millivolt. Well, it depends. But anyway, let's say just very small signal is here. And then, so this capacitor, what they do is that they just only accept AC signal. So let's say the VG, VG looks like some signal from amplifier, antenna. And then, so this point is important. This DC voltage is V bias because we have this circuit. So this circuit select, choose, set the kind of operating point. So that's we call V bias. And then output is also the same. For output, if you see the V out, the way how it works is also like this. Maybe a little larger amplitude because it's amplifier. But still the point is this DC voltage, there's something like DC bias is here. We will learn how this VO is chosen, but at this moment, just accept it. The point is we have some DC operating point, and then the signal is moving around it. It's like a pivot. So that's what it says. Here, when we see here, we have a certain operating point. So this one, a certain operating point for devices. In our case, this would be NMOS, right? Because we have NMOS here. And then this certain operating point corresponds to VG and VD, which is VO, V out, right? And what was the VG? VG is V bias. I'm only talking about operating point. And then VD, operating point of VD is some value VBO. So these are what we call a quiescent here, this quiescent voltage and current. So we have something like operating point most for a usual analog circuit. Okay, so we did kind of first thing. We discussed about how to choose a Quiescent operating point. That's how it works. And then what was the next one? We need to replace the nonlinear elements to linear elements. So let's talk about here. What's our nonlinear elements here? NMOS, right? NMOS is nonlinear elements in this circuit. And just assuming that our IV curve looks like this. So this is our NMOS IV curve. It's not linear, right? Because when you say if something is linear, that means it's just straight line. That's what we call linear. For example, I equal some constant A times V. This is linear, but this graph is not linear, right? This graph is not linear. It has some curve. So we need to replace this NMOS nonlinear element to something linear element. This kind of analysis process is what we call small signal approximation. As I said, in many cases for analog circuit, the voltage and current only vary slightly. This is what we called here, this point, it just operating like this. And this point is also like operating here. So we only have a small signal, like variation, but we have a like large operating DC point. So that's why we call this as, what we're doing is small signal here. And then I think what we should do next is this make a linear approximation, because we already got an operating point, and then this is what we should do. And that our target is this one. So our nonlinear, let's say we have nonlinear NMOS, and then we need to make this NMOS to linear. We want to approximate these nonlinear elements with linear. And then we'll talk about that in the next slide. So this is our like IV curve for our nonlinear NMOS, assuming this is our nonlinear NMOS. And this point, not here, okay, this is our NMOS. And we got here, and then this is, let's say, VG, and then it was V bias, right? And the way how we linearize the circuit is, this NMOS is just use a here slope, and then we calculate this slope, and then we say it's G. So what we get is this I equal VG, and then G, its order is amps over voltage, and this is what we call a small signal conductance. So this is how we usually do. Just use slope. And then here the other thing is that we're not caring about this part. We don't care about this. We only care about this very small area. And then the reason why it's possible is that usually the analog circuit has the actually varying input. They have a small signal range. And then you might wonder, what if the analog circuit doesn't have like small signal operation? What if the analog circuit actually really have a huge signal? What I'm saying is, like in previous case, it was like this, right? And then V in, V out. Our assumption was, oh, this input is really small, and then this output is also small. The question could be, what if we just apply really huge input and then output is also really huge? In this case, small signal model is not cannot like predict the circuit behavior well. then that will make things complicated. But that do happen. But in our scope, well, we usually care about small signal input. So again, the point is that it's not like always. Input is not always small signal. Sometimes it's large signal. But in our lecture, we usually assume that signal is small. This is just assumption. It really depends on application. The other thing would be small signal parameters usually use lowercase. So for example, here we are saying I equal G V. We're not saying like I equal GV. We're not doing it. We just use small signal letter. Before moving forward to MOSFET small signal model, let's just briefly talk about superposition. This is very useful characteristic of linear circuit. So for example here, what it says is that, okay, assuming that we want to calculate the I here, and then there's two voltage source. Since this resistor is linear, what we can do is like this, R and then V1, and then assuming that I1. And also we say V2, same R, and then I2. So I1 is R over V1, and I2 is R over V2. And what superposition makes possible is that we can just add this up. So total I would be I1 plus I2. So which is V1 over R plus V2 over R. So this is what superposition does. And then this is very useful. We will use these properties in circuit analysis. But this is only applicable for linear. For example, here we have non-linear, which is diode. You know, diode. So diode looks like this. If voltage and then I. So basically, its current suddenly goes up when voltage is above certain voltage. So this is not linear, right? Linear should be just linear should be just straight line, but this is not linear. In this case, we cannot do this. In this case, we cannot like make a superposition on this, and like V2. Well, we cannot do this. Here I1, I2. So total I, and then this is I. Total I is not this because this diode is not linear. Let's talk about small signal model for MOSFET. We kind of learned that how to make how to model certain circuit as small signal model. First one is to find a quiescent operating point, which is a DC bias point, and then the second one is to substitute nonlinear model, nonlinear component to linear component. So, what about MOSFET? The MOSFET will have these three components. So this will be, we'll call this GM, and then this will be RO, and this will be GMB. We'll learn how it looks like. So this non-linear MOSFET will change with some GM, RO, and GMB. And then it becomes linear. This is our goal. And here, each of these relates to how a small change of voltage between the source and another terminal changes ID. It just means that ID is function of like GM and RO and GMB and maybe VG or something like that. So we'll just represent the ID using these terms. And this table shows our three parameters. Here, so actually this is 1 over R0. So in previous slide I said RO because that's what we usually use. But
Yeah, this is just RO2. RO. And the name is output conductance, or we also call this as output resistance. I think we mostly use this as output resistor, output resistance. This is what we're gonna use more often. And the change ID due to change in, it means that it's because of VDS. Here, so VDS is the voltage across here. Um, so this symbol, which is we call output conductance or output resistance, it's a it's a function. It's how the change of VDS translated to change in ID. And then the next one is transconductance. I think this is number one important thing. Um, this is corresponds to VGS. Um, well, I would just say in because it should be lowercase VDS. And so it corresponds to VGS, which means that the plus minus VGS. And it's like GM becomes like delta ID or ID. Again, so these column shows a small signal. They are not like bias or something. It's just small signal thing. For example, here, I think I'm saying it multiple times. So let's say this is V bias and VG as actually here. So this is VGS. Okay, this small signal. And then often we sometimes just plot it at zero, around zero, like 0 volt and then VGS. So in long story short, VGS is a small signal part of the input, VG. And GMB, this is body effect transconductance. Here, this is body effect transconductance. And then it is related to GBS, so body substrate voltage, also a small signal. First, let's talk about transconductance, which is GM. This is the most important parameter, I'll say. And then let's see how it comes. So here, the definition of GM is this. So let's see the transistor, and here maybe source D, and this is drain. Gate. And then the current here is ID, right? Well, so what is GM? GM means GM is the so it means differentiation, right? Differentiate ID over GS. So VGS. It means like how much of ID, how much of current changes over VGS changes. And again, so let's say for example here, what it does actually is that so VG. So here's let's say VGS. So VGS actually works like this. So it's like it consists of V bias, which is DC, and then like VGS. You see, I use a small letter here. So it basically means that how much of current changes with this small signal VGS change. And then here under constant VDS and VBS. So this is important because usually this gate input goes to gate. So usually, not always, but usually V input goes to the gate, and then output would be represented by the function of current. So that's like if we apply input, then how much of current, output changes. So here's some math, and I think this is really important math actually. Um, I still use this like differentiation quite often when design circuit. It's kind of easy. So here we already learned that ID is represented like this. So this is in saturation. So in saturation, we're talking about the transconductance in saturation. So let's do differentiation, VGS. So it becomes what? Mu n COX W over L VGS minus VTH. Um, at this point, let's just ignore the channel length modulation in this part. So this is very important equation. We need to memorize it. But there's multiple other forms that represent this GM. So let's look at this in the next slides. For transconductance, as I said, the one format that we had was GM. This is from previous slide. This is delta ID, delta VGS, and this is mu n COX and W over L, and then VGS minus VTH, right? This is our first form, but we can have a different kind of form. So for example, what was the ID? ID was 1 over 2 mu n COX W over L VGS minus VTH, right? We're just ignoring channel X modulation, so this one we're just ignoring. Okay, and let's do some kind of math. So this thing can be, so what happened is 2ID times, okay, if you do some COX over ID, if you do this, then what happened is mu n COX 0 square and then VGS minus VTH square, right? So if we do a root in both, then mu n COX over WID would be GM, because this is the same as this, right? So the equation 3 is the other form of GM. And so depending on the situation, sometimes we use this form of GM, or sometimes we use this equation 3 form of GM. The other thing would be this one. We can just, you can do some calculation, and then if you do the math, then this is what we got. So there's the three types of equation form. Here's a summarize for transconductance. This is form 1, this is form 2, this is form 3. Very important equations. You need to know how to derive this form from the most ID equation. This is very important, so be very used to it. Then why do we need three forms of transconductance equation? We'll learn it in the further lecture, but let's just see the third form of GM. GM looks like this, right? So, and then we call this VGS minus VTH as overdrive voltage, VOV. This is very frequently used, so be aware of it. What happened is GM increases as VGS minus VTH or VOV decreases, right? Because it's in denominator. Let's assume that we want to increase GM. So if GM is large, then what's good? So GM was like how current changes, right? How current changes over VGS. So it's usually give us like better better gain, larger gain, because we control NMOS with GM. So having large GM is good. So okay, let's say, oh, we want to increase GM by reducing VGS minus VTH, but we want to keep the current. How do we do it? To do so, what we have to do is, it turns out we need some W, bigger W, and like smaller L. So we have to change the design. I mean, change the design parameter. What in this case, but is it good? Can you just reduce VGS minus VTH as well, like just we want? You know, you can also think about it. This is the side story. Lower VOV is good sometimes because of the limited VDD. I'm saying we have like headroom over. So what I'm saying is here usually 0 volt and then let's say 1 volt. 1 volt is analog supply. Then when we design the circuit, what happens is the overdrive is like headroom. We call this as headroom in our real design. So let's say some NMOS occupies this kind of voltage, and then the other NMOS occupies this, and then maybe PMOS occupies this. So there's a concept of headroom. It means that each NMOS or each MOSFET, they should have a limited like voltage usage, and this headroom is related to VOV. So VOV, small VOV is good for us because we can have larger headroom. I will come back this later, but my point is um, reducing VOV definitely has an advantage. Okay, but anyway, let's come back to here. What is the limit? Let's just remove it. What is the limit? Can we just reduce VOV as much as we want? No. We usually want to keep the overdrive like over, let's say, 100 millivolt. It depends on the technology. For strong inversion, it's good for a MOSFET operation. And then we also need high VGS minus VTH for good current matching. This is kind of advanced concept. Um, so there's current mirror. We're gonna learn current mirror. So, and then what it says is here, VTH. Um, so there's a kind of mismatch between MOSFETs. So for example, here, let's say we have this MOSFET, NMOS here, and then right next to it, there's another exactly same NMOS. Usually what we want is we want this like the same. We want this the same due to various reasons. But for example, one reason can be we want the current same. Um, we'll learn it later. This is current mirror. But to match these things, we need like high enough VGS minus VTH for matching. So just point here is that we cannot have too small VOV. We need that for certain purposes. The next thing will be GM of bipolar transistor. That's represented like this, just for your information. Let's talk about transconductance in triode region. As we said, transconductance is GM, and triode region, what was it? This is very important. VGS is larger than VDS, right? So VDS is not big enough. That's what we call triode region, linear region also. This is also linear region. Um, so starting with the equation looks like this. What we do is, so GM, the definition is the same. Differentiate ID over VGS, and this would be mu n COX W over L and VDS, right? Is it? Yes, it is, because yeah, VDS is here. Yeah, and what was the saturation region thing? So for saturation region, GM was mu n COX W over L, and then VGS minus VTH. So in trial region, suddenly GM is not function of VGS. This is function of VDS. So this is kind of resistor, you see, because if there is MOSFET and then if this is D and then S, and GM is like um, so GM is like 1 over R kind of, right? So it's I mean here what I don't say is um, so okay, let's see about this. Okay, so in this case, if we increase VDS, which is plus minus VDS, if we increase this value, then current is increasing. And what does it mean? I mean proportionally. So this is kind of resistor, right? And that's why we also call this as linear region. So the current is proportional to VDS, which is just R, right? Current is proportional to this voltage. So just this is like resistor as a linear resistor or linear region literally. This slide shows the same. Um, we just write down the equation that we calculated before. This part is kind of interesting. So let's say some VGS is fixed, and let's say we change VDS. So here, what was the GM in triode region? This was mu n CoX W over L VDS, right? And then in saturation region, GM was mu n CoX W over L minus VGS minus VTH. And what about this point? This point, VDS, this is VGS minus VTH. So in this point, VGS minus VTH is equal to VDS. So if we plot GM and then this is triode, this is saturation. So GM just increased linearly, right? Because you see VDS is a proportional. And then in saturation, it's just a constant line because in this case we are not changing VGS and VTH. So, but in reality, we have a channel length modulation. So this is not actually a straight line, but since at this moment we are ignoring it, so what it gives is that give us the idea is that even if we increase VDS, GM is kind of stayed constant. Next one is output resistance. So what did we learn so far? We learned GM, right? We are learning RO, which is GO, also 1 over GO, and then we're gonna learn about GMB. And to remind you, the reason why we are studying this is that we want to make a MOSFET small signal model, model, um, and then that small signal model has these three components. That's why we're learning, just to remind you. So output resistance, this is also a very important thing. Output resistance is from channel length modulation. When we calculate GM in previous slides, did we consider about channel length modulation? We didn't. We assumed that there isn't channel length modulation. So those equations maybe not 100% correct, but still does a decent job. So, but anyway, let's come back to output resistance. What it says is, so here, so output conductance is change in like VDS. So, and it means that ID is a function of VDS in saturation. Okay. So let's see the graph here. Let me just remove this. Maybe I can write it down again. So we have GM and RO and GMB, and we are learning these three for a MOSFET small signal model. That's our goal. So we learned about GM already, and then we are learning about RO. So when we see this MOSFET graph, this is IV curve. In ideally, even if we increase VDS in saturation region, current is not increasing, current stays the same. But that's not the case in real life because of this channel length modulation. So actually the current is increasing. Um, if you see the ID curve, this part shows VDS, this contribution. If we increase VDS, what happens is ID is also increasing, right? So we represent those characteristic as output resistance. Let's do some math here. In this, suddenly we consider channel length modulation, right? Channel length, what? Channel, well, I'll just say channel length modulation. Okay? Because output resistance only exists when channel length modulation is there. So this is it's come from channel length modulation. Oh, not this one. Channel length modulation. You know, in our previous case in GM, we didn't consider channel length modulation, right? But then suddenly, why do you care about channel length modulation? So in circuit design, there's a lot of approximation. This is also our kind of approximation or when we think about like GM, transconductance. We're not gonna consider VDS, I mean channel length modulation because it's too complicated. That's our assumption. And in output resistance, oh, but actually this channel length modulation plays an important role, I mean kind of a um, key role. So in this time, we're gonna consider this channel length modulation. So this kind of thing happens a lot as a circuit designer. Again, for the actual circuit, their model is very complicated. It's really hard to calculate the exact number. So what we do is we always do a simulation. So this kind of calculation is for to see a trend, to get an intuition on circuit design. So anyway, in output resistance, we are considering this channel length modulation. And then the GO is the derivative of ID over VDS. So we can just calculate it, and this is actually looks like ID times lambda. Again, ID, this is ID when we ignore channel length modulation. I know in this above here, we consider channel length modulation, but suddenly we just ignore channel length modulation. Again, this happens a lot. This is just try to make the equation simple and then get a very nice intuition. So um, usually, so okay, GO, let's say GO is lambda ID, but usually what we use is 1 over lambda ID, and then this RO is what we use usually. So that's why we call this as output resistance. We will see how it looks like in a NMOS small signal model. So the third one, as I said, we learned about GM, which is related to VGS. And then we also learned about GO, which is equal to 1 over RO, output resistance, which is a function of VDS. And now we got another thing, GMB, which is a function of VBS. Okay. In saturation, let's just ignore channel length modulation here. There's nothing, so ignore channel length modulation. Actually, VTH is affected by body effect or change in VBS. So VTH is function of VBS. What it means is that VTH differentiated by VBS isn't zero. Okay, so it means that ID over VBS isn't zero. So we need something. I mean, we have something. Okay. Here's the equation that we can calculate. You can refer to textbook. But here for me, I'll just skip it. With a complicated calculation in previous slide, we got this form. Let's see how it works. So GMB, the body effect transconductance, GMB, is proportional to GM. And then this eta is a constant, usually in the range of this part. But also this eta is kind of function of ESV, but as I said here, what we're saying is this is a small signal model, so we assume this is kind of constant in terms of large signal. And they have a same sign. So it means that this body effect transconductance, it give us like a kind of free gain. Finally, we got all three components. These three. We do a lot of math and well, as I said, this is for our small signal model. And the reason why in here in this slide now we have the three components, which is GM and GO and GMB. For low frequency, this may kind of you may wonder why they put low frequency. Because if it goes to high frequency, we need to consider about capacitor. So that's it. We still gonna use these three components for high frequency. It just says in low frequency model, these three are kind of just um, the only components. And there are the other components such as gate resistance. We'll see the example here. And then again here, because it's low frequency, we also ignore all capacitances. Now let's see how, okay, we just do a lot of calculation and then let's see how actually the MOSFET small signal model looks like. Finally, this is our NMOS transistor small signal model. Maybe you can watch the lecture again once you learn about this structure. Maybe if you're confused about GM or RGB, this kind of thing, maybe you can just go back. But anyway, this is our ultimate small signal model finally, and then we call this as low frequency because there's no capacitor, right? We actually use this model a lot in circuit design. So just review GM was the over VGS, and then GM is here, right? And GMB is here. So this is why it says GMB is kind of helping GM because they have a same current direction. And RO is here. That's why we call this as output resistance. So I think this is very important. And then this model is also very important. I'll say very important. We will use it a lot of times. And yeah, well, the other thing would be eta would be like, let's say just 0.25, something like that. And there's the other part that may good to consider is this VBS equals 0. So this part, sometimes you're not using this part because when this bulk is connected to source, right? There's a case like this, right? And then VBS is 0, so we just ignore it, and then it turns out like this. I think this is more kind of commonly used. For example, if I say the circuit, for example, we will learn this in next lecture. But for example, here we can see the common source amplifier VO. In this case, this NMOS, the bulk is connected to source. So we don't have VB in there. VBS is 0. So we are ignoring the this part, body effect, transconductance. This slide shows the high frequency small signal model. I'll say high frequency. The point here is that we see a lot of caps, right? We just add a lot of caps. This is also we're going to use this. Usually we don't use it. We don't see this. We don't see this. This GS and then GD is kind of important. So I think we will see the example that when this capacitance is necessary. So this is for high frequency. When we want to consider like what's the speed of the circuit, what's the maximum operating frequency, something like that. We'll come back using this capacitance. In the textbook, there was one interesting problem, so I brought it in our small signal model. So small signal model was just looked like this, right? Um, like RO, GM, VGS, and VGS, D, G, and S. But here we just say, oh, there's nothing. This is just shorted. But actually, there's RG here, and that's we call as gate series resistance. Um, the reason I brought this example is that the layout actually help us to make circuit better. We also talked about this before. We talked about a parasitic capacitance, and then the parasitic capacitance is different depending on how we draw the layout, right? So this is the same. Let's see A and B. The point is here, this is just W, but here is W over 2. So it looks different, but actually circuit is the same because they have finger. It's folding or finger, the kind of layout, finger. So if we draw so this is W is well W is W actually, and this one because this is they are parallel connected. This is the same. They also have a W as W is W. Well, I would say let's say just W1 W1. This is also W1 because we connect the two MOSFET in parallel. So their schematic is might be the same, but when we consider about gate resistance, they are different. For example, so this is G, this is gate. From here to here at the very end, it has a long line, right? So it has some like trouble to get there. I'm not gonna say trouble, but it has some larger resistance. What's 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 I mean the cons? It's RC constant is bad. So I'm saying is if you want to change the voltage here, like at this node, at this part, the voltage has some delay because of the resistance. But let's see this case. If we just change voltage here in gate, so this is gate, their length from here to here, I mean this length becomes half. So if we know represent it in circuit, then the gate resistance is half, and here is G. So um, this is better. This is better. It's kind of fast. It can operate. Let's see, just this is faster operation because of less gate resistance. So the point here is that layout. I will say the layout. Let's just write it down. So key point here, layout can impact circuit performance. We're not covering layout in this lecture, but this is a key, very also important message. Layout matters. Here's some example. We're gonna draw this kind of things a lot. Let's see. So plus minus nmos here, and this was gate, right? And so here is vin, vin, and here was what? GMV V1, GMV1, and we also see R0 and here let's say RD. Here's RD, and then this is V out. You see the difference here between that? So I'll just say it V out. I write it down in small, uh, lower letter. And here, this is also actually V in. You see the difference here? Where is this V bias? That's one of the key point here. So when we move to small signal, we are not caring about DC voltage. Okay, so we remove this and we only have V in. But in this case, it seems like this V bias is totally ignored. Do you think it is? No, we actually consider this V bias. Where? This is a very important question. And then we'll cover this in our in-person class too. This V bias is actually impacting this one, this GM. Okay, this V bias is impacting this G1. So GM is function of V bias. So even though when we draw a small signal model, we kind of remove this V bias, but actually we consider that V bias in terms of this small signal parameter. We'll come back again in-person lecture because this is very important. And here's a PMOS small signal model. They are identical. Just try to, you can just try to draw NMOS model. So it use some square, but it doesn't matter. Some people just use square. So like this. This is NMOS, right? G, D, and S. And VGS plus minus VGS. Okay? And R0 and then GMB, VBS. So they're kind of look the same, but a little bit different. It may cause you a confusion, but it's okay. We will use it a lot later, so we can get used to it.
This is the end of lecture. What we learned today, we learned about MOSFET capacitances. Caps in MOSFET are not linear. This is important. So that's what makes the circuit design tricky. And caps have different values depending on its operating region. Okay. And the next one, MOSFET small signal model. I think the key point here is that why do we need small signal model? We need a small signal model for easier circuit analysis. That's our ultimate goal because our MOSFET is not linear, not like resistor, not like capacitor, not like inductor. MOSFET is not linear. It means that the MOSFET operation depends on its operating volt point, linear region, saturation region. Even in saturation region, its operation is different. So um, to make the analysis easier, we use MOSFET small signal model, and then we replace each small signal model. We replace MOSFET with linear components. And then that linear component consists of GM, RO, and GMB. And then we can draw a small signal model MOSFET. So we'll practice it in in-person lecture. We'll draw a lot of small signal model because that's really important in circuit design.